with a balance of matter, okay? Well, so a stream of air plus water, it's coming into this point, which is, I'm gonna call it one. It's already called being one, okay? And it has certain conditions of temperature and pressure, and they already giving me this batch process of 100 moles going in. And then you have this stream two, and then you have this stream three. What it basically says is that there is an amount of air plus water going at two and just water going at three, okay? So if you see here, or at least if you can read the instructions, so T1 equals to 80 degrees Celsius and P1 equals to 1.5 atmospheres, okay? So that's what we have. And at two, what we have here is 30 degrees Celsius, okay? And pressure, yeah, it's a different pressure. It's actually 2.5. It's a higher pressure. So that's what we have here. And that's the basic idea. And I think it's also, you can infer also that this thing is actually, yeah, still T2 and P2 we already have here. So, okay, so those are the conditions that we have here. What they're asking you to get, okay, it's what is this molar composition of water in the whole mixture, and also air composition, a molar air composition in this mixture, okay? The same thing they're gonna be asked here, what about this molar composition here? And here you don't need to get the molar composition. You're gonna put here something, well, then this thing is just one because it's just water, okay? Now what I'm gonna do here is that, so A is gonna be air, okay? I'm gonna use that one, and W is gonna be water, okay? So that's actually what's happening here. There's a twist in this problem, and the problem is that they are giving you several choices, okay, for relative humidity at the beginning. So at the beginning, we have this C percentage of relative humidity. So it's gonna change, okay? I'm gonna do for 15 and for 25 and for 50% what is going on here. So that's basically the idea. I'm gonna start with the end of this problem. The end of this problem, it's actually something better because first of all, it's not changing. The beginning of the problem is changing. So the conditions at the beginning, they are changing, they are varying. Therefore, I'm gonna go with the last one, the last part. So with that in mind, what I'm gonna get here is that, oh, I'm gonna put it here. So I'm gonna put it here. So I have these conditions, right? So for these conditions, this thing, or what the problem is telling me, it is that this stream two, it's saturated. Okay, so here it says that it's saturated. That means that PV2, okay, so the pressure of vapor of this water is actually the same conditions of PG, which is called PG in psychrometry, or maybe in steam table language, it's saturation pressure, okay? So this is what I know, that basically when you have this stuff, so phi at 2 equals to 100%, and that means by definition that PV divided by PG, so this one is 1, therefore pressure, vapor, and saturation pressure is the same one, okay? That's what they are actually telling you. So the way to find this is that you're gonna go to a certain thing. So you go to steam tables and find that 30 degrees Celsius. You have a saturation pressure for vapor. These are steam tables for water, and you will have a value of 4.2 and 47 kilopascals. Okay, so this one is actually PV2. So 4.247 kilopascals. Okay, so now you know how much pressure you have. Now, in order to find y, yeah, of the, oh yeah, this is important. So the molar composition of water at 2, it's easy to find because I already know how much push the vapor is doing to the walls of this stream, okay, to the walls of the pipe of the stream, divided by total pressure. So it's basically an amount of how much amount of water I have at 2 regarding the total pressure. Okay, that's the kind of the idea that we're gonna get. And now from here, what I'm gonna put is this 4.47 kilopascals divided by total pressure. And total pressure is 2.5. That's the atmospheres, but I need to put it in kilopascals, or I want look at this in kilopascals. So this thing would be 101.325 kilopascals, because 1 atmosphere is 101.325 kilopascals. And therefore, after all this, I already had this value. So this value, well, I'm gonna put it. I'm gonna arrange this later. But so far, I have this value of 0.020 1676. Okay, so that's the molar composition of water at 2, and therefore I already can get how much molar composition of air I have in this same stream, and in this one it's just 1 minus of the molar composition of water. Therefore, this is 0.98323. Okay, so this thing won't change. This thing will stay the same. Okay, so that's one important thing to have. Okay, so that's what's happening there. Now, let's just go to my one part. So my one part is gonna be changing. So sorry about that. But before I'm gonna do that, before I'm gonna do that, I'm gonna go to the basics. So for the basics, I know that the amount of moles going out at 1 equals to the amount of moles at 2 and then plus 3. Okay, there is no other way. Well, there could be another way if we had a reaction, but I don't have any reaction here. I'm assuming there are no reactions. Therefore, this thing is fulfilled. I already know that this guy is 100 moles, but I don't know how much of these guys are. Now I'm going to go with air. Take a look at this. If I'm going to go with air, I'm going to say, well, you know what? I'm going to say that the amount of moles of air going at 1, okay, this is what I'm trying to write here, should be equal to the amount of air going at 2. There is no air going at 3. There is just water at 3. Therefore, I can establish this. Okay, so from the get-go, I can get this, maybe I can get this value from here, and I just will equalize to this value over there. Okay, so if I found how much there is of air here, I will find how much of air is going at 2. And with that, I will know how much N2 I have, because I can put here that N2 is going to be equal to Na2 plus NaW2. Okay, and if you know a little bit more about this, this is just N2 multiplied by AY2 plus N2 AW2. And I already have these fellas just because of my analysis with the steam tables. Oh, by the way, I know that you can get it with the steam tables, but if you are not familiarized with the steam tables, you can get it, for example, with the Antoine equation. So the Antoine equation, it's an equation that will give you the pressure, the vapor pressure of almost any substance if you have this A, B, and C. So the logarithm of the 10 logarithm of the pressure of vapor equals to A plus, I'm sorry, not plus, minus BT plus C. Okay, and there are Antoine equations when you're putting the information with Kelvin, with degrees Celsius, and you will get, depends on which A, B, and C you are putting that. But anyway, you need to put the temperature as we did here. I didn't put this T equals to 30 degrees in any equation, but I just use the steam tables. But you can also use it with Antoine equation, and this Antoine equation will provide you this P set, this PV that we got. Okay, so from here you can put in explicit form. This will be 10 to the, well, A minus B T plus C, and you need to check in your tables of Antoine equation constants what are the units that you need to put this T, and what are the units that the pressure will give you, because Antoine equation is an empirical equation. Okay, so you need to be aware of, okay, how much this temperature should be in which units, and what would be the units of pressure after I solved with this equation. Okay, so that's the drill with the Antoine equation, which is a great tool if you don't use water. So it's if you use water, well, you can use steam tables, but if you don't use water, like in the chemical industry that you have several, I would say thousands or hundreds of substances, well, maybe you can have 100 of tables of A, B, and C for each one of those substances. Okay, so going back to this place, now what I'm gonna do here is that I should have this fella, okay? So I'm gonna put here at 1. Let's just see what's happening and what are the units that I have at 1. So N1 equals to 100 moles, okay? So I got that. And also I need to know that N1, I'm gonna put it here. N1 is, just go to the basics. N1 should be made of the one of the air, of the moles of air plus the moles of water, okay? So those things are basic. Maybe they don't help me at all right now, but for me, those things are important so I can know what I'm doing. Now, Na1 equals to AA1 times Na1, and NaW1 equals to AW1 N1, okay? So maybe this doesn't mean much, but at least for me, it gives me a structure. I know that this is true. I don't know if this will help me or not, but at least it gives me certain structure. So I already know this value, okay? So now I will try to find other things. So take a look. I have this one and I have this one. So maybe those things will help me in order to find certain things. Take a look. Maybe I can do this. So P1 is going to be P1 is going to be equal to 10 to the A minus B T plus C. So I can use Antoine equation again in order to find for water. If I just change this T, and instead of using 80 degrees, I'm sorry, 30 degrees Celsius, I'm going to use 80 degrees Celsius. And that will give me the pressure of vapor here that maybe I can use around at this part, okay? So that's one of the things that I can use. That's one way to do it. And another way to do it with steam tables, okay? So steam tables, if you know steam tables, they are very helpful when you have water, which is in this case. So for steam tables, you know that your temperature is 80 degrees Celsius, and you're gonna get Psat. So this saturation pressure, which in psychrometry they put as PG, okay? So this saturated pressure at 80 degrees Celsius is gonna be the same, or it could be a little bit different, but it should be the same value that you have here. So in my case, using steam tables, I have that Psat at this 80 degrees Celsius. I have that this thing is 47.416 kilopascals. So it should be kind of the same thing that you get here. So 47.416 kilopascals, okay? So that's what you have here. Um, Okay, so after this, you need to use your C. This one C is the relative humidity that you have. So you have three cases. So it's gonna be a little bit, bothersome. One, and then case two, and then case three. But all these three cases are for just point one or stream one. Okay. So let's just see if we can do it that way. So phi for this one is 15%, okay? So remember the definition of phi, which is PV divided by PG. So I already have this filling, I already have this guy. Therefore, I can get this PV with no problem. And I'm also gonna get it when this phi, instead of 15%, is 25%. And the same thing when this relative humidity is 50%. Okay, so maybe you will start to notice that PV will increase because P side is the same for all of these cases. So this saturation pressure is going to be the same for case one, case two, and case three, but the vapor pressure is not going to be the same one. Therefore, let me just put PV1 for case one equals to, I already have this stuff, so let me just try to find it. And what I will get out of this is going to be, where you are, this is 7.11, 7.20, 4 kilopascals. For this case, PV1, in this case, I have 11.84 kilopascals. And for this case, I have that the vapor pressure is 23.708 kilopascals. So again, how did I get to this number? So for example, I got that this 0.25 should be equal to PV that I don't know divided by this value of where am I? Where am I? 0.1, right? So 0.1. Okay, so this one, yeah. So 47.416 kilopascals. Okay, and that's the amount. That's how I got this. Once I got this fella, and the same here. So remember, PG equals to 47.416 41, 6 kilopascals, okay? So that's kind of the idea of how you do this stuff. Okay, so now that I have the vapor pressure for each one of these cases, it's the same stream, but they are different cases. Just, I don't know, maybe for something that they ask you to see, what would happen if the relative humidity is increasing? What do you think it will happen? Well, okay, so now you know how much is PV1, and therefore you can already get this fella. So which is going to be PV1 divided by total pressure, the same one here for this case, and the same one here, you get the picture, right? And the same one for this case, okay? So this one shouldn't be any problem. Now, total pressure, please remember, a total pressure is the total pressure of this stream, which is 1.5 in atmosphere, but I need to change it. I need to change it to kilopascal. So long story short, 7.1124 divided by 1.5 and 101.325 kilopascals. So I already have these numbers. Let me just try to make a division over here so I can have these numbers. Therefore, this is 0.046468. This is for this fella. This one is for this case. This one is 0.078. And for this one, the molar composition of water at stream 1 is this one, okay? So there are different molar compositions because the relative humidity is different. That's what's happening. Therefore, with those informations, I know now 3 different molar compositions for air because there are 3 different amounts of water in this stream. So for this one, this is 0.9532, and this one is 0.9222, and this one is okay, so 0.84844. Okay, now that I have this, you know, everything, now that I already have this stuff, I can go back to point 1 and see if I can fulfill some of these equations. Maybe, I don't know, maybe this one. So yeah, you can already do that. And again, for all these 3 different cases, you will have different amounts of values. So moles of air at stream 1 equals to moles of air at stream 2, because at 3, there is no air there. So for this one, maybe you know, or you can do that. This one is A1 times N1. Therefore, I'm going to put all NA1s that I know here, and this is 95.32. It's just, you know, it's just multiplying this by 100, so maybe it's not very complicated. The same thing is going to happen here, so you can, you know, you can put forward to this video, because now I'm just putting these numbers out there, okay? So this is Na1, which is equal to Na2. But before I do that, let me just put here NW1, which equals to the molar composition of water at 1 multiplied by the number of moles that went in. Therefore, I already have these Na1s here for all these 3 cases, and it's just writing numbers like that. So NaW1 equals to, what do I have here? Oh, I didn't put it. So I didn't put these ones. Jesus. Well, okay, but you can see that this should be 100 minus 90.22, and this one is Na1 equals to 100 minus 84.4, okay? So I don't have those numbers because actually they are not asking me that. By the way, they are asking you, hey, please, can you give me the molar composition of water here and the molar composition of air at 1? Well, yeah, I have 3 different molar compositions for you. This one is the first result for 15% of relative humidity. This one is the other result for 25%, and this one is a result for 50%, okay? So all those things are already known. Now, the other thing that they're asking you is about 2. So point 2, let's just go for point 2. And also what they're asking is, okay, so how much moles of water are going at 3? Okay, so those are the things that we can do. Let's just go for 2, okay? So I'm gonna change it and go for 2 and just recap a little bit what would happen at 2. I'm gonna use another color. So for another color. So another color would mean, just to make it a little bit more appealing, hopefully. So at 2, remember you have 30 degrees Celsius. You have that, by the way, at 2, this one is 100%. And maybe you would say, well, you know what? There's more air. I'm sorry, there's more water here because it's more moist. right? You have more relative humidity. And I will tell you, well, no, because actually the temperature went lower. So this low value of 30 degrees Celsius will get you to a smaller amount of water in air. Okay. If you had 80 degrees Celsius, so at 80 degrees Celsius, you have much content of water in that same stream of air. And now you have lowered the amount of water. It looks contradictory, right? Because maybe you will feel that because of this number, you have more amount of water, but this is another guy that you should take into consideration, okay? Well, okay, so at 2, you can do this. So I already have Na1 and should be equal to Na2. Therefore, I already know that my Na2 is 95.32 moles, okay? And well, and then what? Well, you can write the basics. So Na2 equals to Na1 plus Na, yeah, I'm sorry, for Na2. This is correct, but let me just put it this way. We don't know this fella, okay? And yeah, I have this one, and I don't know what to do with this guy over here. Well, if you know the molar composition, you should remember that NaW2 equals to YW2 multiplied by the Na2. And I think you know this fella, okay? So you already had that one. So that shouldn't be a problem, okay? So you already have that thing. But you also can do this Na2 equals to Ya2 multiplied by Na2. You can also do that, okay? So what I'm gonna do here is to use that information. So remember that we already had this information here. This is the thing that we got from point 2 at the beginning of the problem. So we already have the amount of well, the molar composition of air and the molar composition of water. And I'm gonna use, I already can use it. So yes, I have this fella, okay, and yes, I have this one, okay, so that shouldn't be a problem. And I also have this guy. Therefore, what I'm going to do is to get N2 from this equation. So I couldn't do anything with this one. I think I couldn't do anything with this one. So this one was the one that get me out of this mess, okay? So you should always put all the information in formulas that you have. Maybe it seems like a mess, but at least there's the possibility that one of them will help you to get out of the problem that you're getting, okay? So N2 should be N2 divided Na2 divided by Ay2. So this number is well, long story short, what I have here is that it will depend, okay? So hopefully you can, well, okay, so what I'm gonna do here is that this one is 0.98323, and this Na2 equals to what I have here as 95.32. Please remember again that this value will change for case 1, case 2, and sorry about the mess, but then case 3, because the amount of moles of air will change depending on the relative humidity at stream 1, okay? So with this value, I have that N2 equals to 96.9045 moles, okay? And that's the amount of moles that I have completely going at 2. Therefore, I know that N3 by using global molar, the molar balance, okay, I know that this is N1 minus N2. Therefore, this one, N3, it's the amount of moles of water that are going through stream 3. Therefore, this is 90, oh, sorry, 100 minus 96.95. Therefore, I have for this fella that N3 equals to 3.054 moles. Okay, so those are the moles that I have. In this case, you can do the same thing. What changes for each one of those cases are Na2. So for Na2, if you kind of remember what was going on, this is 92.22 moles, or you can get it in this, for this case, Na2 equals to 84.4 moles. Remember, it was just multiplying 100. So that's how we got it. And after doing all this stuff, you can get that Na3. I'm not going to do the whole thing, but Na3 equals, well, you know what? I'm going to do it. Why not? So I'm going to put here that Na2 equals, for this case, Na2 is equals to 93.793 moles, of course, moles. And this one is Na2 equals to, let's see, 85.84 moles. Okay, so that's what I have. Therefore, N3, it's just 100 minus this. So this one is 6.071 more moles going out in this case. And maybe the tendency will give me that I'm condensating more water at 3 in the last case, which is 14.1604 moles. Okay, so those are the condensation part. That's the last question that they're asking in this problem. By the way, they are asking you this AY2 and YW2, but you already got them from here. And this case 2, sorry, this is not case 2, but for this stream 2, you don't have any different cases. It's just stream 2, and that's it. Well, okay, so I will see you in another video.